Okay, so the next part of this is Program Optimization II, which is SIMD. So to recap, our achievable performance so far is right at our throughput bound, which is good. But you're limited now by the throughput of the functional unit, right? So each floating point multiply can issue one operation per cycle, and because you have two floating point multiplication units on that Intel Core processor, this allows you to do two floating point operations per cycle, which is great. But you want more. So for example, if you have 8K resolution in your video, 8K TVs are coming soon, so if they're powered by Intel processors, well, hopefully the SIMD is going to keep up with that. But if you're talking about 7,000 by 4,000 frames at 60 frames per second, you require operations on pixel data that are massively parallel. So you can't afford to have a single CPU with two floating point units on there processing your video. Just can't keep up. All right. So our best achievable performance is really not going to be adequate when you're talking about this kind of data. So specifically, video isn't the only place where this happens. Almost all of these modern applications that we're talking about are going to use large amounts of data requiring a single operation across all of them. So for example, video encoding, even on your phone, when your phone records a video and wants to encode it into some compressed form, it's going to need to do this frame differencing to, delta encoding, for example. It's going to need to do a vector subtraction of one frame to another. It would be nice if you just had one instruction and then it would operate on bunches of the data rather than just serially. Image fade in and fade out for video effects. Overlays in games. Matrix computations for scientific computations, for example. In security, encryption and decryption in bulk. So Google is now encryption by default, SSL by or TLS by default. So it's delivering a lot. YouTube over SSL, TLS, requires a highly parallel encryption and decryption mechanism. If you're doing deep learning, the neural networks that are underneath, single operation, multiple data, that's basically what they do. You would want them all to be vectorized. You don't want serial operation on these things. So in general, anytime you see an algorithm that has characteristics of data access in a regular pattern, and operation on fixed data types, like either 8 bits, 16 bits, or 32-bit data types, and then have an operating paradigm where you're streaming data through fixed operations, basically, fixed operation pipeline. And we call this data flow operation. These are things that are amenable for single instruction, multiple data. Okay. So, and this is also known as vectored instructions. So everything before was one instruction per data location. And with SIMD, you have one instruction that can operate over multiple sequential data locations. These are the new classes of instructions that I'm going to introduce to you. Before, there was only ever one data location, but now we're talking about multiple data locations. And to support this, both the execution unit and the registers themselves must be wide. They have to be wider than your single scalar registers were, right? If you want to do 16 8-byte operations, well, you need a honking register to do that. Load all of that into that register and then do those in parallel. So you need these wide registers. There are examples of SIMD instructions from all the way back into the early 90s with MMX that Intel introduced. And so these are some of the code names for each of these SIMD instruction sets that we'll talk about. Okay, so here's an example in C. I have this loop that is taking two arrays, A and B, adding them together and leaving the result in A. And so this is doing operations one at a time. You could unroll this operation like this to take these things 4 at a time. What you would want to do to vectorize this is something that looks like this, where instead of these instructions being serial, you want to have the vector a of I to I plus 3 to be set equal to that plus b of I to I plus 3. This is the idea of SIMD sort of execution. And it goes sort of hand in hand with loop unrolling, right? So if you could have unrolled this thing 4 ways, and then you have this 4 wide vector that you're doing the operation on instead, that's the idea.
You don't need assembly. You don't actually need to hand code assembly into this?
Maybe. Well, you guys will. That's your homework. Sometimes you can get the compiler. You can get the compiler to vector auto-vectorize. There's actually a GCC beyond 4.3 will auto-vectorize. I don't want you guys to do that for your homework. You guys have to manually. It's not that much assembly, but it is some assembly. But that would be the point of it.
There's some assembly required?
There's some, yeah. Yeah, maybe I should show the people who made that joke. Yeah. All right. Yeah, some assembly required. So the general idea of SIMD is that you have these wide registers, and then you do a parallel operation on vectors of the registers. So here are 2 registers and color-coded operands. So within that register, you have 4 operands, and then you add the yellow to the yellow, the red to the red, the green to the green, and the blue to the blue. Similarly, if you have a multiply, 2 registers, this is a vector multiply. You multiply the yellows together, the reds together, the greens together, and the blues together. So that's pretty simple. This is sort of the timeline of all of these vectorized instructions. I'm not going to go through here, but we'll incrementally talk about the important parts of this. Okay, so we'll start with the MMX extensions. And the idea of MMX, this was back when we only had 32-bit registers. So the idea here was the floating point unit. The old floating point unit had 64-bit registers to support the double. And so back in the 90s, they decided to try and reuse the floating point registers, which were 64-bit, to do vectorized integer operations. So this is the very first attempt at this. The reason why they didn't want to establish brand new vector registers was to save the context switching, right? Because in a context switch, you're always going to save ST0 to ST7. These were the old floating point registers. So if you could get away with not changing the overhead on the context switch, you would. And so they just decided to reuse these registers. But the pain of this is that you could no longer do a floating point operation and a vectorized integer operation at the same time, right? Because you overloaded it. Okay. But these are the instructions that it supported. You can do 8 single byte additions. So you have a 64-bit register. So 8 cars could be stored in that register, and you could do a parallel add on those bytes, on 8 bytes. You could also do a parallel add of 4 words. So these are 16-bit words, and you can do 4 of them there because it's a 64-bit register. Or you could just do a parallel add, a packed add, which means you take the 2 32-bit quantities and you add them together. All right, so that's the simplest form of SIMD with MMX. The next iteration of this was SSE, and this is called Streaming SIMD Extensions. They increased the register size, and they finally went over to larger independent registers. So this is where you get this XMM0, the MM0 register. So these are the new vectorized registers used for SIMD, XMM0 to XMM7. And there are 128 bits now. And they started out with 8, but eventually they doubled the number of XMM registers in SSE3 because they were being used so much. One of the things when you do these vectorized arithmetic operations is that every single operation in that vector is going to set its own flags, right? So you need to check for overflow on these operations, So there's a parallel flag register that's associated with this. We're not going to get into that, though. Yeah. But if you needed to, that's what you would have to read that register, yeah.
Where would you find more information about that?
Oh, the Intel architecture manual. It's like, just don't print it on a lab printer. Cat would get very mad at you. In fact, I think you have a 500-page quota a month. Yeah, you would have to print. You print half of it this month, and you can print the other half next month.
I thought we had a
Per term?
Yeah.
Okay, next quarter.
Or just get like, you could just paralyze it, just have you and your 10 buddies go over. And
Yeah, well, like, each one of you can print 20 and then combine. OIT? There you go. Then go to OIT. Yeah.
So this is kind of like how the unions, you could operate on multiple different interpretations of the same data.
That's exactly correct. Yeah. You can treat it as a vector of bytes, a vector of shorts, a vector of ints, a vector of longs. Yes, that's
As
correct.
long as your operation is commutative upon that binary number, you can do that in as many vectorizations as you can and keep it consistent, right? So like if you're adding two bytes, if all you care about is like the byte is like
Yeah, I'm going to say yes.
say yes to what?
I don't know what I said yes to, but I said yes. I don't know. I think he'll clarify if he needs to. The thing with the SSE is that now it supports vectored floating point operations. So for scientific computations in particular, you can finally do vectored floating point. It adds a streaming support. So one of the issues is feeding these registers with data. Like, you're basically calling instructions to load from memory these XMM registers. And in order to make that fast, if you're doing this in sequence, if you're accessing a huge array of data sequentially, then the processor can do sort of like prefetching on the data that you're about to get. So there's this prefetching and cache control support to keep those registers from starving. So yeah. Because you're basically, I mean, this is a wide, you're loading in each one of these registers a lot in a single instruction. So you need that support. They added these permutation operations. So especially for encryption, what you want to do is parallel permutations of data, like bit flipping and these sorts of things. That's what an encryption algorithm would want to do, shuffle your bits, for example. If you could do those in parallel, you can speed up your encryption algorithm. Horizontal operations within the vector, so finding the min and the max element across your data in your vector, that's supported. It actually encodes the sum of absolute differences in terms of the for video encoding, and that's the frame differencing sort of stuff that I mentioned earlier. And then graphics building blocks, support for dot product, and this is actually what we're going to use for your assignment. Yeah.
And that's why the video encoding accelerator and like all this other hardware stuff, they're just making like special cases, but they just like speed it way up, which is why like newer CPUs play like newer stuff way better. So if you have like a CPU from 2016 or whatever, you can play H265 without killing your battery.
Yep.
But if you have like a CPU from 2014, it'll kill your battery really fast if you try to play anything above 1080p.
Yeah, so these instructions will make a difference on video playback, for sure. For sure. Okay. So all x86-64 CPUs support SSE, so all of your stuff in front of you, unless you're really running old school stuff, that'd be like a decade old, maybe. The last non-x86-64 processor is probably a decade old. I am assuming you have this for your homework. Actually, I'm assuming you have the next version. Sorry, because what your homework should run on the Linux lab machines, and then those have the actually 256-bit data registers. They have the next register set. Yeah.
Does the Atom support that too?
No. So I believe the Atom went to the i386 architecture. I don't know how far up from the i386 they went. I don't think they did this. You can check though, but I think they went back to i386, a stripped down i386 for low power. Yeah, so this is not power-wise. SIMD is not cheap power-wise, so that's why they probably got rid of it.
But it's still more efficient for like hard-coded software, like video rendering or stuff like that. So they'll have video routines in there.
So here's the thing: a lot of times that circuitry is not being used, and then it's a power draw to keep the circuitry on.
Yeah.
So yes, for when it's actually doing what it's intended to do, it might be power efficient versus sequential execution. But then you have that functionality in your chip all the time. Maybe not a good thing. Okay. Yes.
So the inevitable question here is, if we keep increasing the size of the register by 2 each generation, what's to stop us from just making like kilobyte registers and doing this on?
Oh, we're almost there. We're at 512.
Okay, or just keep going higher.
I don't know what's going to stop these guys. I don't know, but I'll teach it, whatever it is.
Like encoding a petabyte of data. in
Oh,
seconds.
yeah. Let's not get silly.
So there's the cost aspect, right? And there's the actual physical space that we can actually write these in. And so like right now our tools can only write down to a couple microns, which sounds like really awesome, but
No, so the parallel, this is all going on underneath. So it's a matter of getting the memory to feed the darn thing.
yeah.
So you're asking on a single load for 512 bits, which is a lot more than you used to ask, and we saw that memory is the bottleneck. So there's a reason why when you look at the real estate on an Intel CPU, like 70% of it is memory. Well, before they put the on-chip graphics card on there, but like if you get rid of the graphics, like if you look at the die, it's mostly memory because they got to feed this thing. Okay, so SSE3 is the next iteration of this, and it doubled the number of registers. So this is the register set for SSE3. You got XMM0 all the way to XMM15. I should use the pointer. They're all 128 bits. They're all caller saved. So, and when you want to pass floating point parameters, you pass them in order from 0 up to 15. The floating point return value is XMM0, which is as part of your homework binary. You should have been looking into XMM0 for the return value. Adam uses SSE3.
Yeah, that's SE3, which is
Streaming
a
SSE. Yeah, 3. Yeah, that's the version after SSE3. But yeah, all right. Adam does use SSE. Yeah, good. So they added that back.
Go back to what you were talking about with you said that we have to use XMM0 for one of our homework assignments?
Yeah, return the floating point value in XMM0. Did I give you that one?
Yeah.
The floating point, the last one.
Yeah.
For a meta CTF.
Yeah, there's a meta CTF binary that uses XMM.
Okay.
Did I not
No,
distribute
it's
that? It's there?
We just haven't
Oh,
gotten
yeah, okay. Well, there is one. So now you can do that one. All right. Actually, yeah, that's not in. This is chapter 5. I should have given you that earlier because that's labeled chapter 3.
There is some sort of floating point in chapter 3.
Oh, where it talks about returning it in XMM0.
Well,
Did I put that in there?
Floating points in
You guys
chapter
knew
3.
that already? No?
Well,
You don't
knew
remember it.
that, no.
All right. Well, if not, let me know. I gotta fix that. I'll move the binary out actually, or I'll move this content in. Okay, so this is what it looks like when you vectorize this 128-bit register. You can put 16 bytes in it, 8 shorts, or 4 ints in it. You could put 4 single precision floats or 2 doubles. You can also use these registers as scalar registers for floating point operands. So if you only had a scalar floating point operation, you would just use the low part of the XMM register to hold that operand. Okay? And the same with the double. Okay, so now we're going to get to what it looks like in assembly. So we'll start with the moves, and these are SSE3 instructions. The notation here, so the move command you're familiar with, the first S says I am going to move a single scalar. So the first letter is whether or not it's vectored or scalar. So this says I'm going to move a scalar single precision floating point number. So the last letter is what is the data type that I'm moving. So this says single precision. So scalar single precision versus move scalar double precision. So this is the move double, this is the move float. All right, that's the notation. Likewise, the add, subtract, multiply, divide, max, min, and square root. This is scalar single precision. This is scalar double precision. So that's how you're parsing these instructions. And so anytime you see an op with an S after it, that's scalar. And we're going to show you scalar operations and vector operations side by side. Here's an example of an inner loop. So what we have is, it's similar to the combine for, where you're taking this result, this float result, and you're combining it with, you're accumulating the products of array X and Y together and adding it to the result. And if you look at this, you're doing, you're clearing out the register by doing an XOR. You're doing a move scalar single precision, and you're getting that this is the base X plus 4 times the index, and you're moving it into XMM1, and then you're multiplying, a scalar multiply, single precision, the element in Y. So that's what this assembly instruction does, and then you add XMM1 to XMM0. This is an add single precision scalar, and then you continue. So does everyone see that this assembly implements that scalar? Yes.
On your previous slide,
Mm-hmm.
that's all Intel architecture, not AT&T, right? Because you had your destination source into destination being one.
This is the effect. I didn't tell you the format of the source. This is source destination.
Oh, okay. So it's still whatever.
It's still
format
source to
you use.
destination.
Okay. I just want to make sure I just thought the effect was
Yeah.
the same methodology.
Okay, so this is very equivalent to the integer loop that we've been seeing, right? Okay, so let's revisit these instructions for the vectorized versions. So move SS, scalar single precision, move SD, scalar double precision. The vectorized version of this is move aligned packed single precision, move aligned packed double precision, move APS and move APD. This says move a vector of 128 bits to and from a register and assume that these memory locations are aligned. And again, we talked about alignment in structs. Initially, it was very important for these moves to happen from aligned memory boundaries, right? So you could get it all in a row. Like in particular, you wanted them all to be in the same cache line, for example. And that making sure that it was aligned allowed that execution to complete optimally. Okay. So those are our moves. Did you have a question? So those are the move instructions. Now for the arithmetic operations, we had add scalar single precision and add scalar double precision. To do the vectorized version of this, we have add packed vector single precision data types. Because there's different ways you can break up that vector. You could do bytes, ints, shorts. So you actually need to you have to specify the kind of instruction you want on that vector. So we have this explosion, right? Because you have, add, subtract, multiply, increment, decrement, and then you have a vector of cars, a vector of shorts, a vector of ints, a vector of floats, a vector of doubles. Those are all separate instructions, right? Because you're treating the vector differently. All right. The bottom one is add packed double precision. So that's how you parse this instruction. Okay. So here's an example of a scalar add single precision short, XMM0 to XMM1. And this is what you have. Everything up here in gray is a don't care. And then the two scalars are presumed to be loaded in XMM0 and XMM1, and this is what this instruction does. If you had an add PS XMM0 XMM1, then basically what you're doing is you're taking this vector in parallel and adding it together and accumulating it on XMM1.
Why would we use the XMM zeros for scalars? Can we just use like RAX and those registers if we're just doing the scalar add?
The RAX register is for integer operands typically. So these are ending up being implemented in the floating point unit, close to the floating point unit. So that's typically why the floating point registers have a separate naming. They used to have this ST0 to ST7 notation, but then they used to have. So it used to be a chip coprocessor off of the original CPU, and they would have separate registers and separate ways to access. And then it went on chip. They still had separate registers, and now it's still on chip, but you would definitely want a separate one. The FPU is probably storing these. I mean, this is where the registers are physically located, and it makes sense. Well, it made sense not to repurpose the RAX registers for the floating point stuff. Yeah.
Does that mean, you were talking about like back when what they used to do? Is that back when they had like logic boards and stuff like that, or is that after logic boards?
Don't know. Yeah.
Don't know what.
Computer.
Logic boards. Yeah, I'm not sure what you mean by logic boards, because logic boards have been around for a while.
Yeah. But you used to, like, now we just have a motherboard which has all the logic circuits.
Well, it was basically on the same motherboard, so.
Yeah.
Okay. So how do you get at this? So I'm building you up to actually using this. Yeah, I got 30 minutes. So one way to do this is to find libraries that have been compiled with SSE support. Find someone else who has optimized their code to use SSE, and then use that code. Another way is through what they call compiler intrinsics. So the issue here is that anytime a new SIMD instruction set gets released, the compiler hasn't caught up to produce the code that will use those instructions. So temporarily, you have to either write the embedded assembly yourself, or you sometimes in compilers, they have these intrinsics. And so these intrinsics are basically macros that allow you to access the embedded assembly through your programming language.
That's just really pretty wrappers, really.
Yeah, it's a wrapper around, a pretty wrapper around the embedded assembly that they provide you.
And that's straight substitution.
Yeah, so here's an example of using it in, this is a Microsoft example. So they use this data type as a 128-bit data type, and then they add two 128-bit vectors as a packed single precision vector. So these are 8 floats, and then if you have 3 of these vectors, then you would call this intrinsic to add A and B and accumulate this on C, and then this is what it will do. Okay, so that's compiler intrinsic. Since GCC 4.1, auto vectorization is now implemented, so you can use -O3 or this -F tree vectorize. The issues with C is, and we saw this earlier, memory aliasing. C cannot make an optimization if it doesn't know that vectors don't overlap. Now, you and I are like, of course my vectors won't overlap, but we have to tell the compiler that, otherwise it can't make that assumption, and it can't do this auto-vectorization if it might be the case that some of these vectors overlap, because then it would have to do those serially to get the thing correct. Okay. The other thing that it requires is alignment, and this is for earlier implementations of SSE. SSE now has an unaligned instruction. They figured out how to do things more efficiently on the unaligned. And so the alignment specifies that the vector allows you to use the move APS and the move APD instructions because these required that the data was aligned on 16-byte boundaries, and so you have to instruct the compiler to explicitly align your data on these boundaries. And we'll see this when we look at the code that's coming up.
Can you run vector instructions on non-primitive data types like structures?
No, I do not think you can.
Can't what?
Run vector instructions on non-vector. It makes no sense. All of these are tied to primitive data types. So we'll see in all the instructions. They're doubles, single precisions, they're bytes, they're shorts, they're always primitive data types on the vector. Okay, so here is something you can write. Add scalar. It takes pointers to arrays, double arrays A, B, and C, and then you write this as scalar additions, and you call add scalar, and you can compile this, and you get the code on the right. So again, scalar moves of doubles, scalar adds of doubles, and then for each array element, this is the 0, this is A of 1 and B of 1, this is A of 2, B of 2, this is A of 3, B of 3. So you see how that's done one data element at a time. So we would like to vectorize that. So this is one way you can do it, and it looks ugly, but I'm going to explain. In C99, and this is the one time I move over to C99 and use C99, there is this restrict keyword. The restrict keyword denotes non-overlapping addresses. So it tells the compiler that there are no aliases here. So when I say restrict A, this tells the compiler, assume that there's only one reference to A, the array A, and that I have it, and I'm giving it to you. Likewise, restrict B and restrict C, these are all, I only have a single reference to that, so this deletes out the aliasing, or it tells the compiler that you have hand-coded it to make sure that those don't overlap. The other thing is, this is a compiler intrinsic that says align A on a 16-byte boundary. Same with B and C. And that's to a... Yeah.
It's not aligned, it's just saying assume it's aligned on these boundaries, right?
Yeah.
You're
it's
not having to move it for you.
No, it's saying if you do allocate this on 16-byte boundaries so that...
So wouldn't that have to be outside of the function?
Well, if you're compiling this, so if this is if these are external symbols that you're passing in, then you tell the compiler, if this isn't a separate C file, you just say generate code assuming that these are aligned, and then I'll make sure in whatever file I have A, B, and C defined to make sure that those are aligned.
So this is how you do vector instructions using just C code?
Yeah, just C, to get the compiler to try and generate exactly what you want, to coax the compiler into generating the vector code. And so everything else is the same. So I've done these operations before. This is like scalar. I have the same arrays, and I say add vector FGH, and then I compile this, and here's where the dash M flag matters. I'm going to compile this saying, hey, assume I have a Core i7, which has SSE, and I will get what's in... do I have it up? No. Show this to you momentarily. So this example is up there if you so if I look at this make file, I have two things here. I have the SSE. So I take that the SIMD file. Let me show you the SIMD file. The SIMD file has both the vector version and the scalar version, and the vector version's got the compiler hints. And then I do add scalar and add vector, and I call this. And I'm going to compile this C file two ways. One that says, assume I have a Core i7 and assume I have a Core AVX2. So this is the Haswell chip, I believe. And then this is a earlier generation Core i7 that has SSE3. So it's not going to be able to vectorize as well on this one versus the upper one. And then I have the scalar implementation there, so you can see the scalar the scalar assembly side by side with the vectorized. So I'm going to build this and take a look at SSE.S. So let's go down to the scalar first. This is exactly what you saw before. Single instruction or single data element at a time. If you go up here in the add vector, you can see the packed, this unaligned packed move, and another unaligned packed move, followed by, or three of them, and then you do an add of XMM1 to XMM0, and then you use these two vectors and then do another add. So you see the vectorized add. So it's doing elements 0 and 1 together, and then 1 and 2, no, 2 and 3 together is basically what these two are. And that's because it only has 128 bits. So you have doubles, so it can only do 2 doubles at a time. So this is why it's paired up. So you need 2 separate packed adds in order to implement this add vector. That.
I always give notes of those. You never know.
Okay. And I'll show you the other one after I get to it, the AVX one. But let's go back. Okay, so this is what it's doing. Well, so this was before they supported unaligned packed. You're basically handling, you're loading A of 23, you're loading A of 01 in these two registers. You're accumulating B of 23 and B of 01 onto those two registers, and then you're storing those results in the final two registers down here. All right. Are there any questions about this? This makes sense?
So if you didn't have the restrict keyword there, it wouldn't generate the vectors?
It wouldn't generate the vectors.
Assume that they're not
Overlapping. Correct. And this is very similar to the combined for thing that we saw earlier. It's similar construct there. Okay, so the generation beyond SSE3 was this AVX, Advanced Vector Instructions extensions. So it doubled the size of the registers, and then instead of XMM0, they use YMM0. So YMM0 specifies the full 256 bits. You can still address the low 128 bits as XMM0. So with these registers, now you can do 8 32-bit integers as a vector. That's a lot of integers. Or 8 single precision floats. You can also do 4 double precision floats or 4 64-bit integers because we're on a 64-bit integer architecture. Okay. There's also what's known as gather support to load memory from non-contiguous memory. So this is where the UPD came from. So this vectorized move upd says, give me 256 bits from of doubles and load it into the register. Okay. The other thing that it added was this fused multiply add operation. So if you're doing something like this, where you have some accumulator and you're adding a product of B times C to it, this can be done in a single instruction. So this is your homework, basically. You're going to be doing this operation using embedded assembly, using a full vector of I think it's either doubles or floats. I forget which one. So that's what you'll be doing. Okay, so get you to the syntax. So we saw add single precision. Add scalar single precision, add scalar double precision. We went to SSE and we said add packed single precision, add packed double precision. And now we have this 256-bit packed add. And so we do a V add packed S. So all the V's mean 256 bits. Right? AS. What would AS?
Or sorry, SS. Or it'd be the.
No, I think they would just reuse that.
Yeah.
All right. Okay. back to that example. This was compiled with -mR core i7, and you saw that it was doing these 4 doubles in pairs because there was only 128 bits in these registers. So we should, with AVX2, be able to do this all in one shot. So when you compile this code with this -mR core AVX2, this is what you get. You get this vectorized load of A0 to A3 into YMM1, a vectorized load of B03 to YMM0. You get this packed add of this vector, and then you have this move that stores it out into C03. So again, this can be done with one add now, one vectorized add rather than all those instructions that we had earlier in the scalar version. And so that's what this example shows you. So these are the instructions that implement the vectored version for AVX. And then you see the scalar. This is an improvement over the scalar version, right, which is down here.
Did you hand code those, or were those
Generated
generated by the compiler?
by the compiler from this C file, right? So using just this C file, you can get the compiler. You can coax the vectorized implementation out of the compiler.
So our homework is just to get it to coax the compiler?
No, I'm going to have you embed it. I don't think the compiler would automatically. Maybe you can coax the compiler to automatically use the fuse multiply add, and then you would embed that in assembly into the C file. But you're going to submit a C file, so you could coax the compiler, figure out what the assembly is, and then embed that. I'm not going to know. No one's going to know, but it should definitely be. It should use the 256 bits. Like, I'll know whether or not you're using that. Actually, your performance numbers will show whether or not you're using the right vectorized implementation, and whether or not you're using the fused multiply instruction, which we'll get to.
The 256-bit will be twice as fast on average.
Then the 128. Yep.
A little over because you're also doing
Yep.
memory loads.
Correct.
One memory load per generation.
Okay, so when you do add vectorized instructions, you can get pretty darn good numbers. So this is 0.06, 0.24, 0.25, 0.16. So yeah, this is pretty fast. All right. So the next iteration, and some of you might have one. I don't know who just bought a laptop.
This is in Xeon and
Oh, this is on servers, actually.
Yeah,
They
servers.
actually, I read that they intentionally turned it off on desktop machine. Desktop.
yeah.
Because it just pulls so much power.
No, I think they want to upsell you.
What they do is it's so expensive now. It's like make individual CPUs or whatever. That every single CPU they make is like a Xeon
That's
or
it.
whatever. Whatever it gets pinned down to, the best performing ones get turned to the computer one, to the server ones. Then the next best ones, they have half the features turned off and they're turned into i7s. And then
Yeah.
the really shitty i7s get turned into i5s. And the really
Yeah.
shitty
So they
i5s
cripple.
get turned into
They have
i7s.
one design, and then they cripple it to downsell. I guess you could call it downselling. On how much you're paying. Yeah.
But also like,
Well, I would imagine they can turn off the circuitry to give you power savings as well.
yeah.
So,
But also like it depends on how perfectly it was made. So like Intel has made less than 5 perfect CPUs ever.
okay, I need to rush through here, so I have to get to your homework instructions.
Right.
So yeah, this is the next generation, 512 bits, 8 doubles or 8 longs. That's a lot of vectors. Detecting if it's supported, there are the CPU ID instruction is one way that the CPU would tell you what features it has. Another way is through this program, which calls CPU ID in embedded assembly. You notice embedded assembly, you get all the bits in registers, and then based on the register positions, different bits mean different things are supported. Since you guys all know bit operations and you know embedded assembly, this program is knowable for you, and that's actually the source code down there. And on Linux, you can do cat proc CPU info, and that program, the proc file system, will parse the CPU ID bits for you and tell you that, yes, this has AVX, it has AVX2, it has SSE4, SSE3, etc. Now, homework. Your homework is to do a vectorized version of a fuse, multiply, add function. So you're going to have this vector similar to the ones we've been using that have a length and a pointer to an array of doubles. We're going to give you the scalar fuse, multiply, add loop. So in particular, it's going to call this scalar FMA embedded assembly routine, and we're going to show you how we're going to give you the assembly code for the scalar implementation of this fuse, multiply, add, and we're going to ask you to write the vectorized version of it.
Thank you so much.
Okay, so this is what the fused multiply add operation is. You take A of I and you accumulate onto it the product of BI and CI. That's what you'll be doing. So here is the embedded, this is the scalar FMA implementation that we give you. So within this function, this is a move single precision, scalar double precision into MM0, and then MM1 and MM2. This gets A, B, and C, whichever those elements are, based on those pointers. And then this is a fused multiply add operands 2, 3, and 1. This is operand order in this instruction set. You can ignore that for now, but that's what that is. Scalar, so single precision, single value, double precision, XMM1, XMM2, and XMM0. This says, based on this ordering, you're going to take A, which is the last one, and you're going to add B times C to it. That's how you parse that. And then you're going to store it. This is the store command. And then you're going to add 8 to each one because you have now updated the index. You've gotten 8 bytes beyond where you were before. So you increment the pointer to the next object. And then you can loop, like for the length of this, right? So loop, you don't have to use loop in your program, but loop just says take what's in ECX and use that as a counter and go this many times. So in ECX, the reason why it's implicit here is because length is your 4th parameter, and your 4th parameter is stored in what register? ECX or RCX. Why did
ECX?
Yeah, ECX. All right. Well, if that's an int or a long, so that's what this loop is implicitly using RCX as a counter, which is why this assembly is sort of cheating. Like it's using information about that length as part of this loop instruction, and I haven't even given you this loop instruction, but now I have, so that's what it does. So that's what it's doing. You don't necessarily have to use this construct. You could use your for loops and compares and your conditional jumps and your compares and those sorts of things. Okay, so your homework is to implement the equivalent function using AVX2 or Haswell. This is the function prototype. You get double vector A, B, and C. You have to implement this in submission.c, and it has to run on the Linux lab machines. And you are allowed to mix embedded assembly with C code just as long as you have managed to use this instruction to speed up your code. So here is the single precision fuse multiply add on your double. That is what's in the scalar implementation. I want you to refactor the scalar implementation to use the packed version. No, you have to actually load it appropriately and update the pointers, and yeah, it's not going to be as simple. Yeah. Okay. So some. Should I, 6 minutes. All right. Some things that you have to do. So instead of move scalar double, you need to move a packed double vector of 256 bits. So this is your instruction that you need to use. And you need to use that in combination with this thing, and then you're okay. So that's your homework for Tuesday, I think.
Yeah.
Back to the original assembly.
This is why I was like trying to look at this.
So we're gonna have to swap out the move SD.
Mm-hmm.
Put in that new instruction.
Mm-hmm.
So we really just have to replace this stuff. All of it.
And you got to make sure you've updated these things appropriately, that kind of stuff.
Otherwise, they're gonna get overlap.
Well, it doesn't even compile. I tried to compile it.
My code doesn't compile. Let me get on that.
Why you redid it? Because I asked you about that, like.
Yeah, it doesn't compile on me, so I was trying to think maybe I was not making something correct. But
Okay. If it doesn't compile, I have to fix it.
I mean, just have a look. Maybe it's me, but I mean, I just have it on Linux and I
The
tried.
Linux lab. Linux
Yeah.
lab.
Yeah.
Okay. Right. I have to look at that. Okay. So if that's still not enough parallelism for you, and if it isn't for most people, there is the GPU stuff. Using GPUs for general purpose computing. That's the Karen's course. So using your graphics card as general purpose computing tasks. So this is the basis for deep learning for all the self-driving cars that you see out there, the VR applications. This is a YouTube talk by the CEO of NVIDIA, talking about the actual underlying sort of the SDK that is being used to get this to work on NVIDIA hardware.
So what kind of chips in the using? It's like
Their own.
Okay. But
Yeah.
it's like ARM?
Wait, NVIDIA.
No, they're not ARM. Yeah.
Okay, I was
not
just
at all.
thinking.
Okay. Another thing that you would do, so I didn't talk about encryption or security much, but Intel has now an AES instruction that does one round of AES. And so this is another thing that was added to the Intel architecture. And then I'll end here, and I'll do the rest next time. But now you have enough to do the assignment, assuming I can get it fixed.
Really big instruction for a single.
Okay, what I didn't get to last class is the last bit of program optimization, which is code profiling. There will come a time.
This is chapter 5.
Still chapter 5. Just a tiny bit of chapter 5 before we go on to chapter 6. We talked a little bit about timing in your program. In fact, you did this in the first programming assignment. If you ever get into a code base for high performance computing, you might want to profile your code to figure out what parts of your code are taking up the most time, the most resources. So one way you could do this is to use this read timestamp counter and instrument your code all over the place with these timer measurements, and then see. But this is pretty tricky. It's hard to get right. Another thing you can do is use something like the Unix tool gprof. And what gprof does is that if you compile your program with special profiling options, the compiler will insert into your program code that keeps track of statistics of the execution of your program. And then gprof will pull those out of that, will allow you to parse that after you run it. So that's what I'm going to show you. The example we're going to use is Shakespeare. So you have a program that counts all the word frequencies in a text document and then produces a sorted list of words from most frequent to least frequent. So basically a histogram of all the words in Shakespeare. So the steps of this program: convert all the strings to lowercase, apply a hash function to create a hash table of all the words, and then read the words and insert them into the hash table or update the entry if they already exist in the hash table. So this is mostly list operations and then a counter for each word. And then at the very end, you want to sort all the results to produce this table. So collected works of Shakespeare, 1 million words, 26,000 unique ones. So you do this and it takes maybe 9.2 seconds, but you want to know, well, how did I what's the quality of my implementation? Where are there places that I can optimize my code? And then you would want a tool like gprof to say, okay, well, 95% of your time is spent in this routine. Maybe you should optimize that. Okay. This is how you use it. So gprof, if you compile your program with this -pg flag, that will augment the compiler will augment your program with these timing functions. And the way it works is that it will periodically interrupt your program and then determine what function is currently executing. So it's basically going to sample your program and take statistics out of it. Yes?
Isn't that not, it probably works fine. I'm just isn't that not a very statistically valid measurement methodology? Because that's assuming that, if you have an offset that has some inherently, heuristic issues, some issues built into it, right?
Yeah.
If your program runs every 10 milliseconds, it's maybe on a 10 millisecond duty cycle, then it wouldn't give you very accurate results.
If you have a lot of really small functions, it'll miss a lot of those too.
Well, hopefully you're running it long enough so that the sampling, it's like the Nielsen ratings, right?
Yeah, that's fair.
How many households do they sample? 1,000? And then they generate all the advertising off 1,000 boxes, basically. That's I'm not a statistician. Anyone here? You're okay. All right. What is the sampling rate that you need for a program?
Well, you need simple random sampling, and simple random sampling this would be a bias against anything that runs less than 10 milliseconds. So if you have a process that you're doing a lot, but I don't know, it seems like that could be there. I could see that there could be.
It's only if you are synchronized on this 10 millisecond where you get funny. Yeah. Your modulus is sort of,
What happens if you want to measure
That's
a
not
subroutine that occurs in less than 10 milliseconds or something? And
Well,
get one piece
you will interrupt it, and hopefully by the law of probabilities, eventually you'll interrupt it in that function. That's the idea. Yeah. Okay. So when you execute this program, after you do this compilation, you'll execute this program, and then it executes normally, but then it emits this file, gmon.out, which has all your profiling information. And then if you run gprof on the program, it'll parse gmon.out. It will parse the binary, and it'll produce you a result that you can then reason about. Okay. So you go and you do something. You implement this thing, you profile it, and you get something like this. Hash table add is 1% of the time. Find the element in the hash. Find the element is 4. Lowercase, it's 5%, and then most of it is in the sorting. So you're like, okay, maybe I should work on the sorting algorithm to see if I can make that more efficient. Okay, so there's an example of this in this directory, which I can show you. Which I have up right here. So profile.c. So if you look at these two functions, I'm going to call this, I'll use my cursor. I'm going to call this 30,000 times down here. And then I'm going to accumulate onto y, function 1, the address of x, and then j. And the address, this is just an integer. And the reason I'm doing this is so that the compiler won't optimize it out. So in function 1, I'm just doing an accumulated add onto star x. And then on function 2, I'm doing an accumulated multiply onto star x. Now, we saw last class, when you do this addition and this multiplication on a single accumulator, going through this loop, you're bottlenecked by the latency of the addition and the latency of the multiplication. So, this should take about, the top one should take about 3 cycles per iteration. per element, and then this one should take about 5. And then hopefully gprof will give us numbers that make sense, that are close to that. Of course. So this is it compiles a profile. So the last line compiles profile with the profiling functions, and then I have to do this trick to the compiler of not inlining small functions, because if you don't do that, it'll basically say, oh, function 1, I could just copy and paste that code into main and save myself a function call. So that's what that flag is. And then I'll run the program as normal. And then it'll
basically taking away every single optimization the compiler can possibly do.
Yes, for the sake of an example that will actually work. Why? I don't know if it'll work yet, but will hopefully work. Okay, so then it's done. It produces a result, and then I can run gprof on it. And then it'll parse this information. And, well, the add is slower, but not by much. It takes about half the time. So, questions? Kind of sort of gave you what you wanted. That is code profiling.
What is the or less part of that? Like I see you type that, but I don't know.
This takes the standard out. So in Unix, you can take the standard in and the standard out and move them from command to command using the piping. So this says take all of the output and pipe it into the input of this command. So less is that paging command where you can get a sort of a buffered view of the output. Yeah, that's basically what that is.
You can also do it to a file, like that makes your object a
Yeah.
lot easier to read.
Yeah, if you want to put this into a file, and then you can do less foobar. Same thing. Okay.
Is that data collection done by adding something in the compiler, or is it?
Yeah. So the compiler has to add the code to collect the statistics, and then gprof will sort of help you parse the statistics. All right.